A team of researchers in northeastern China built a piece of material that you could hold in one hand. It weighed almost nothing. It looked like a thin strand of dark fiber, barely visible against the table it sat on. Then they loaded it with force. They kept adding weight. The material did not stretch. It did not bend. It did not deform. According to the published test results, the fiber held a load equivalent to the weight of 12 full-grown elephants before it showed any sign of structural failure. 12 elephants, suspended from something you could lift with 2 fingers. That number alone would be impressive if the material were some exotic new metal alloy produced at enormous cost. But it is not a metal. It contains no iron. It contains no steel. It is made entirely from carbon, the same element found in pencil lead, in charcoal, in the soot on the inside of a chimney. The difference is how the carbon atoms are arranged. And that arrangement is what makes this material, according to the researchers who built it, approximately 8 times stronger than structural steel while weighing roughly 80% less. If those numbers hold up under continued independent testing and real-world deployment, they represent the first serious structural challenge to the material that has held up human civilization for a century and a half. Steel did not earn its dominance through marketing. It earned it by being reliable, predictable, and available at enormous scale for 150 years. Replacing it, or even partially displacing it, requires clearing a bar that no alternative material has ever come close to reaching. And that is exactly what makes the data emerging from China's laboratories so difficult to dismiss. To understand why this matters, you need to understand what steel actually is, why it works, and where it reaches a limit that no amount of engineering can overcome. Because the flaw in steel is not something that was recently discovered. It has been known for decades. It is built into the atomic structure of the metal itself. And for 150 years, nobody could build anything better at a scale that mattered. Steel is an alloy of iron and carbon. When iron ore is heated to extreme temperatures in a blast furnace and combined with a controlled amount of carbon, typically less than 2% by weight, the resulting material gains a combination of strength, hardness, and flexibility that pure iron does not possess. The carbon atoms wedge themselves into the gaps between iron atoms in the crystal lattice, creating internal friction that makes the material resist deformation under load. That is what makes steel strong, and it is what made steel the backbone of every major structure built since the Industrial Revolution. Think about the scale of steel's dominance for a moment. A single modern cargo ship uses over 30,000 tons of steel plate in its hull alone, roughly the weight of 80 fully loaded commercial aircraft. A modern skyscraper can use over 60,000 tons, equivalent to stacking 6 aircraft carriers into a single vertical frame. The Golden Gate Bridge contains approximately 83,000 tons. The world produces roughly 1.9 billion tons of steel every single year, enough to build more than 20,000 Golden Gate Bridges annually. Every year, the entire modern world, its buildings, its bridges, its ships, its rail networks, its pipelines, its vehicles, its machinery, its infrastructure from the smallest bolt to the largest dam, sits on a foundation of steel. No other structural material comes close in terms of volume, versatility, and proven reliability. Steel is not merely dominant. It is so deeply embedded in human civilization that most people cannot conceive of a world that builds with anything else. Questioning steel's position in structural engineering has historically been treated with roughly the same seriousness as questioning whether gravity applies to buildings. The answer was so obvious it did not merit discussion, until someone produced data that made the discussion unavoidable. Engineers love steel for a specific reason beyond just its strength. Steel is predictable. When you apply a load to a steel beam, it behaves in ways that engineers can calculate with extraordinary precision before the beam is ever manufactured. The math works every time. A structural engineer in Shanghai and a structural engineer in Chicago can use the same equations, the same safety factors, and the same material properties to design a bridge that will hold the same weight, flex the same amount under load, and give the same warning signs before it approaches failure. That predictability is not a minor advantage. It is the reason steel has been trusted with human lives for 150 years. Every building code in the world is written around the known behavior of steel under load. Every safety standard assumes steel as the reference material. Replacing it means not just matching its strength, but matching the depth of understanding that 150 years of testing, failure analysis, and accumulated engineering knowledge have produced. And that brings us to the part of this story that the steel industry does not enjoy talking about. Because steel has a fundamental limitation that is built into its atomic structure, and no amount of alloying, heat treatment, or manufacturing precision can fully overcome it. When iron and carbon atoms arrange themselves into a crystal lattice during the steelmaking process, the lattice is never perfect. No matter how carefully the steel is produced, no matter how pure the iron, how controlled the carbon content, how precise the cooling rate, the crystal structure always contains defects. Grain boundaries where different crystal orientations meet. Dislocations where rows of atoms are misaligned by a fraction of an atomic width. Vacancies where atoms are simply missing from positions they should occupy. These defects are invisible to the naked eye. You cannot see them without an electron microscope, but they are always present in every piece of steel ever manufactured in the history of the material. And they are exactly where failure begins. When a load is applied to a piece of steel, the stress concentrates at these microscopic defects. The atoms at a grain boundary or a dislocation experience higher forces than the atoms in the surrounding perfect lattice. Under enough load, the defect grows. A microcrack forms. The crack propagates along the path of least resistance, from one defect to the next, through the weakest points in the crystal structure. Eventually, the accumulated microdamage reaches a critical threshold and the material fails. This is not a manufacturing flaw that can be fixed by building a better factory. It is a fundamental property of how metal atoms arrange themselves into solid structures. Every crystalline metal, steel, aluminum, titanium, copper, contains these defects. The theoretical strength of a perfect iron crystal with no defects at all would be roughly 100 times greater than the strength of the steel beams used in actual buildings. But that perfect crystal does not exist and cannot be manufactured at any useful scale. The gap between theoretical strength and actual strength, a gap of roughly a factor of 100, is the price that every metal pays for the inherent imperfection of its crystal structure. And this gap creates a practical problem that shows up in every structure ever built from steel. Because steel is strong but also heavy, roughly 7,800 kilograms per cubic meter, a significant portion of any steel structure's total load capacity is consumed by supporting its own weight. In a tall building, engineers estimate that up to 60% of the structural budget is spent fighting the weight of the steel itself. The steel that holds up the building also has to hold up the steel that holds up the building. It is a compounding problem. Every additional floor requires not just the steel to support that floor's contents, but additional steel to support the weight of the steel added for the floor below. The taller the building, the more of its total capacity is consumed by self-support rather than useful load. This weight penalty propagates across every application. A ship built from lighter material could carry more cargo per voyage. And in global shipping, where fuel costs represent one of the largest operating expenses, even a 5% reduction in hull weight can translate into millions of dollars in annual fuel savings per vessel across a fleet of hundreds of ships. An aircraft built from lighter material could fly farther on the same fuel load. The aviation industry already pays a premium for carbon fiber composites in aircraft bodies precisely because every kilogram saved in structural weight means one more kilogram of payload or one more kilometer of range. An electric vehicle built from lighter material could drive farther on the same battery charge. And in an industry where battery cost is the single largest barrier to affordability, getting more range from the same battery by reducing vehicle weight is more cost-effective than making the battery larger. A bridge built from lighter material could span a longer distance with fewer supports, reducing the number of foundation piers needed, which in turn reduces the environmental disruption, the construction time, and the total project cost. The economic incentive to escape the strength-to-weight ceiling of steel has been obvious to every structural engineer on Earth for decades. Companies have spent billions chasing incremental improvements, higher-strength steel alloys, advanced aluminum-lithium alloys for aerospace, carbon fiber reinforced polymers for racing cars and aircraft. Each improvement moved the needle slightly. None broke the fundamental ceiling. The problem was never desire. The problem was that nothing else worked at scale while matching steel's combination of strength, predictability, and cost. Carbon fiber composites, developed primarily for aerospace applications beginning in the 1960s and 1970s, offered dramatically better strength-to-weight ratios than steel. But they were expensive to manufacture, difficult to repair, and behaved unpredictably under certain types of loading, particularly impact loading, where carbon fiber composites can shatter catastrophically without the progressive bending and warning that steel provides. Titanium alloys are strong and lightweight, but titanium is expensive, difficult to machine, and available in far smaller quantities than steel. Aluminum alloys are lighter than steel but significantly weaker, requiring larger cross-sections to achieve equivalent load capacity, which partially negates the weight advantage. Every alternative material that engineers evaluated against steel over the past century offered improvements in some dimensions, but came with trade-offs that prevented it from displacing steel as the dominant structural material at industrial scale. Steel's position was protected not just by its own properties, but by the collective weakness of every challenger. Then a team at the Institute of Metal Research at the Chinese Academy of Sciences in Shenyang, working in collaboration with materials engineers from Tsinghua University in Beijing, took a fundamentally different approach to the problem. Instead of trying to make a stronger version of a metal, fighting against the inherent atomic defects that limit every crystalline material, they decided to stop using metal atoms entirely and build a structural material from carbon. This idea is not new. Carbon nanotubes, cylindrical structures made of carbon atoms arranged in a hexagonal pattern, each tube only a few nanometers in diameter, have been known to materials scientists since the 1990s. Individual carbon nanotubes are extraordinarily strong. A single nanotube has a tensile strength that can exceed 100 gigapascals, roughly 250 times stronger than structural steel. The theoretical potential has been known for 30 years. The problem was always the same. Individual nanotubes are tiny. A single tube is thousands of times thinner than a human hair. To build anything useful, a cable, a beam, a structural panel, you need to bundle millions or billions of nanotubes together into a macroscopic fiber or sheet. And every previous attempt to do that ran into the same fatal bottleneck. The individual tubes were unbreakable, but the bonds between them were not. When researchers bundled millions of nanotubes together, the tubes did not connect to each other at the atomic level. They were held together by weak intermolecular forces, van der Waals forces, that are orders of magnitude weaker than the covalent bonds within each individual tube. The result was a material whose individual components were incredibly strong, but whose overall structure was limited by the weakest link, the connections between components. It was like braiding a rope from threads that are individually unbreakable, but using glue between the threads that falls apart under modest tension. The rope is only as strong as the glue, and the glue was never strong enough. For decades, this bundling problem appeared unsolvable. Research groups around the world, in the United States, in Japan, in South Korea, in Europe, published papers, filed patents, and presented conference results on various approaches to improving nanotube-to-nanotube bonding. Some tried chemical vapor deposition techniques to grow tubes in aligned arrays. Some tried spinning nanotubes into yarns using the same principles as textile fiber production. Some tried polymer matrices that embedded nanotubes in a resin, creating a composite rather than a pure nanotube material. Each approach achieved incremental improvements. Some produced fibers with impressive laboratory strength numbers, but none achieved the kind of breakthrough that would make carbon nanotube structural materials competitive with steel at industrial scale, meaning consistent quality, repeatable manufacturing, and sufficient production volume to matter beyond a laboratory demonstration. The fundamental problem remained after 30 years of global research effort and billions of dollars in cumulative funding. The individual tubes were extraordinary. The connections between them were ordinary. And ordinary connections in a structural material mean ordinary performance, regardless of how extraordinary the individual components are. What the Chinese team reportedly achieved, and this is where the published data becomes genuinely remarkable, is a new bonding method that creates direct load transfer pathways between adjacent nanotubes at the atomic level. Instead of relying on weak intermolecular forces to hold the tubes together, Their process creates covalent crosslinks between neighboring tubes, meaning the tubes are connected by the same type of strong chemical bonds that make each individual tube so strong internally. The load applied to the fiber does not stop at the boundary between one tube and the next. It passes through the crosslink and continues into the adjacent tube with minimal loss of force. The weak glue problem is eliminated because the glue has been replaced by bonds that are fundamentally the same strength as the tubes themselves. The practical result, according to the team's published data, is a macroscopic carbon nanotube fiber that retains a meaningful fraction of the theoretical strength of individual nanotubes, enough to achieve approximately 8 times the tensile strength of structural steel at roughly 20% of the weight. The gap between individual nanotube strength and bulk fiber strength has not been fully closed, but it has been narrowed enough to produce a material that dramatically outperforms steel on a strength-to-weight basis at a scale that can be manufactured, handled, and tested using real engineering protocols. And the team did not stop at laboratory data. In what may be the most significant step in this material's development so far, the fiber was tested in a real-world structural application. Cables made from the carbon nanotube material were installed on an ocean monitoring buoy and deployed at a depth of approximately 3,000 meters in open water. The cables were exposed to continuous saltwater immersion, one of the most corrosive environments any material can face, plus pressure cycling from wave action that repeatedly stretched and relaxed the fibers thousands of times per day, temperature fluctuations between warm surface water and cold deep water, and the biological fouling from marine organisms that degrades conventional materials by growing on and into their surface structure. According to the published results, the cables survived 8 months of continuous deployment without a single fiber failure. 8 months at 3,000 meters depth in the open ocean. A senior materials engineer at the monitoring center reportedly told state media that they stopped calling it a laboratory material the day it survived its first full monsoon season on the buoy without a single fiber failure. That is a meaningful statement from someone who works with ocean-deployed equipment every day and understands exactly how aggressively the marine environment destroys materials. The full dataset from that 8-month trial, including tension logs, temperature readings, and inspection photographs, was shared on a national open data platform, allowing independent researchers anywhere in the world to examine the raw numbers rather than relying solely on the team's published conclusions. Making raw field data openly available is significant because it invites scrutiny. A team that publishes only conclusions can control the narrative. A team that publishes raw data is inviting the global research community to check their work. That level of transparency strengthens the credibility of the results considerably. The production process also cleared an important practical hurdle. According to available reporting, the manufacturing method is compatible with existing carbon fiber winding equipment already installed in factories across Jiangsu province in China. This means production does not require building entirely new factories from scratch. Manufacturers can adapt existing equipment, which dramatically shortens the timeline from laboratory demonstration to commercial scale production. The difference between needing a new factory and needing a new tool for an existing factory is often the difference between a decade of waiting and a single year of deployment. And the commercial world has noticed. More than 140 international patent families now cite the core bonding process behind this material. Patents have been filed across China, the United States, Germany, and South Korea. Patent filings at this scale represent genuine financial and legal commitment. Companies do not spend the money and legal resources required for international patent prosecution on technology they consider merely interesting. They spend it on technology they plan to build products around. The specific companies paying attention make the commercial implications concrete. China Baowu Steel Group, which is, ironically, the largest steel producer in the world, announced a $200 million joint research project in early 2026 focused on developing hybrid steel nanotube products. The logic is straightforward and defensive. If carbon nanotube materials are going to displace a portion of the high-performance steel market, the world's largest steel company would rather control that transition from the inside than watch a competitor eat its revenue from the outside. Comac, China's commercial aircraft manufacturer, confirmed it is testing the material for interior structural components on its new narrow-body aircraft program. CATL, the battery manufacturer, disclosed that it is evaluating the material for battery casings, an application where every gram of weight saved in the casing translates directly into additional vehicle range for the same battery chemistry. In South Korea, POSCO, one of the world's largest steelmakers, opened a dedicated testing laboratory specifically to evaluate this material against its own advanced steel alloys. China's Ministry of Industry and Information Technology added advanced carbon nanomaterials to its official list of key strategic materials in 2025. That designation opened access to preferential government loans, faster permitting for manufacturing facilities, and policy support that removes several of the bureaucratic hurdles that typically slow commercial adoption of new materials. Government designation does not guarantee commercial success, but it removes friction from the path in a system where government support can meaningfully accelerate industrial deployment timelines. If production scales according to early investment projections, industry analysts project this material could replace up to 15% of high-performance steel cable applications by 2035. That represents a market currently worth roughly $9 billion annually. And the efficiency benefits extend beyond direct material performance. Lighter structures require less energy to transport, install, and maintain over their operational lifetime. Engineers estimate that a large-scale shift toward this material in aerospace and marine applications could reduce life-cycle carbon emissions by up to 12% per structure, a reduction that comes primarily from eliminating the fuel burned moving unnecessary weight around for decades. But this is where the honest assessment matters. Because the gap between a promising material and a global structural standard is enormous, and the history of advanced materials is littered with technologies that performed brilliantly in the laboratory and failed to achieve meaningful commercial deployment. Production volume is the most immediate constraint. Current output across all Chinese facilities combined reportedly totals approximately 2 tons per month. That is nowhere near the scale required to meaningfully impact global steel demand, which is measured in billions of tons per year. Scaling from 2 tons per month to thousands or millions of tons per year is not just a matter of building more factories. It requires solving supply chain challenges for raw carbon nanotube feedstock, training a workforce in a manufacturing process that barely exists outside of research settings, and establishing quality assurance protocols that produce consistent results across industrial volumes. Quality consistency is the second major challenge. According to available reporting, the tensile strength of the material can vary by as much as 15% between production batches, depending on humidity levels during the bonding process. A 15% variation in strength is manageable in a research context, but potentially dangerous in a structural application where human lives depend on the material meeting its specified performance every time, in every batch, without exception. Steel's advantage is precisely this kind of consistency. A steel beam manufactured in any certified mill in the world will perform within a narrow, well-characterized range of properties because the manufacturing process has been refined and standardized over more than a century. International building codes represent a third barrier. No country outside of China currently has established building codes or structural engineering standards for carbon nanotube-based materials. Any structural application in the United States, the European Union, Japan, or other major construction markets would require years of standardized testing, regulatory review, and code development before the material could legally be used in a load-bearing role. That process cannot be shortcut. It exists specifically to ensure that new materials are safe before they are trusted with human lives. And it takes time, typically 5 to 15 years for a genuinely new material class. Long-term durability data is the fourth and perhaps most fundamental limitation. Nobody has tracked this material through 20 or 30 years of real-world exposure. Steel has been studied through 150 years of documented failure modes. Every bridge collapse, every beam fracture, every fatigue crack has contributed to a body of knowledge that engineers use to predict how steel will behave over decades of service. That accumulated failure data is as important to steel's trustworthiness as its raw strength numbers. This new material has 2 years of published data and 8 months of field testing. That is an excellent start. It is not a substitute for the multi-decade performance history that structural engineers require before specifying a material for critical applications. And there is an American dimension to this story that mirrors patterns seen in other recent technology shifts. Carbon nanotube research has been conducted extensively at American universities and national laboratories for decades. Rice University in Texas, MIT in Massachusetts, and multiple Department of Energy national laboratories have published significant work on nanotube synthesis, characterization, and potential applications. The fundamental science was well understood in American research institutions. What did not happen in the United States was the transition from published research to funded industrial development at the scale required to solve the manufacturing and bonding challenges that kept nanotube materials in the laboratory. American materials companies with existing steel or advanced alloy product lines had limited economic incentive to fund a competing material that could cannibalize their own revenue. A steel company spending $1 billion to develop a material that replaces steel is a company actively working to destroy its own best-selling product, a proposition that no board of directors evaluated on quarterly earnings would approve without extraordinary pressure. Venture capital investment in advanced materials has historically been modest compared to software and biotechnology because the development timelines are longer, often a decade or more, the capital requirements are higher, the regulatory pathway is more complex, and the path to commercial return is less predictable. A software startup can go from prototype to revenue in 18 months. A structural materials company might need 15 years to reach the same milestone. Government industrial policy in the United States has not historically prioritized advanced structural materials with the same intensity that Chinese industrial policy has applied to strategic material categories. The result is a pattern that is becoming familiar across multiple technology domains. American laboratories produce world-class research, and Chinese industrial systems convert that research into commercial products at scale. The science was international. The factories are Chinese. And the gap between those two steps grows wider with each new example. That pattern is not inevitable. It is the product of specific policy choices, funding priorities, and institutional incentive structures that could be changed. But recognizing the pattern is the first step toward changing it, and the carbon nanotube structural material story is the latest and perhaps most consequential example. Because if this material reaches even a fraction of its projected potential, the implications extend well beyond replacing steel cables. Lighter, stronger structural materials change what can be built and where it can be built. Bridges that span longer distances with fewer supports, enabling infrastructure in mountainous regions and island nations where deep water foundation piers are prohibitively expensive. Buildings that rise taller on smaller foundations, reducing the excavation footprint, the concrete volume, and the construction timeline for urban high-rises in cities where available land is measured in square meters rather than acres. Ships that carry more cargo per voyage, amplifying the efficiency of global trade with every crossing. Aircraft that fly farther on less fuel. A 1% reduction in airframe weight translates to approximately a 0.5% reduction in fuel consumption. And across a global fleet of tens of thousands of commercial aircraft flying billions of kilometers annually, that adds up to billions of dollars in fuel savings and millions of tons of reduced carbon emissions. Spacecraft that launch with more payload per kilogram of vehicle weight. The cost of launching material into orbit is measured in thousands of dollars per kilogram, making every gram saved in structural weight directly equivalent to money and mission capability gained. Electric vehicles with lighter frames that extend battery range without increasing battery size or cost, addressing the single biggest consumer objection to electric vehicle adoption. And then there are the applications nobody has fully imagined yet. New structural materials do not just improve existing designs. They enable designs that were previously impossible. The transition from wood and stone to steel did not just make bigger versions of existing buildings. It made skyscrapers, suspension bridges, and ocean-going steel-hulled ships, entire categories of structure that could not exist in the previous material era. A material 8 times stronger than steel at 1/5 the weight does not just improve the current era's designs. It potentially opens a new design era whose defining structures have not been conceived yet, because the engineers who will conceive them have not yet had access to a material with these properties at a usable scale. Steel earned its place through 150 years of proof. It bent before it broke. It warned before it failed. It built the modern world and held it up through earthquakes, hurricanes, and the accumulated wear of a century. No material has ever matched that record. And no honest assessment of this new material should pretend that 2 years of laboratory data and 8 months of ocean testing are equivalent to 150 years of proven structural service. But the numbers this material has posted in those 2 years are numbers that steel never posted in 150. 8 times the strength, 80% less weight, 0 metallic crystal defects, direct atomic level bonding between structural elements, and a raw material, carbon, that is one of the most abundant elements on the surface of the Earth. Steel did not become the foundation of the modern world because it was perfect. It became the foundation because nothing better existed at scale. If something better now exists, even partially, even for specific applications, even at early production volumes, the question is no longer whether the foundation can be improved. The question is how fast. A fiber you can hold in one hand. A load of 12 elephants. A material made from carbon atoms arranged so precisely that the microscopic flaws that limit every metal ever manufactured simply do not exist in its structure. Built in a laboratory in Shenyang, tested at the bottom of the ocean, and backed by the largest steel company on Earth hedging its own future. The strongest material in the world is no longer a metal. It is an arrangement of atoms that someone finally figured out how to hold together. And the country that figured it out is not waiting for anyone else to catch up.